Okay, after reviewing, I've changed my mind. I'm going to do section 2.4 and 2.5 individually. Section 2.5 is only one slide, but it's a lengthy discussion, so I'll break it up. Let's see. Analysis model, particle under constant velocity. An analysis model represents a common situation when solving physics problems. It also represents common types of problems that we have solved before. When you identify an analysis model in a new problem, the solution to the new problem can be modeled after that of previously solved problems. Analysis models help us recognize common situations and guide us towards solution to a problem. An analysis model is a description of the behavior of some physical entity and the interaction between that entity and the environment. When you encounter a new problem, identify fundamental details. Ignore details that are not important. Attempts to recognize which of the situations you have already seen that might be used as a model for the new problem. As an example, if you imagine a car moving along a straight freeway at a constant speed, is it important that it is an automobile? Does that play a part in the problem solution? No. Is it important that it is a freeway? No, that's not important. Answers to both questions are no, but the car moves in a straight line at a constant speed. You can model the automobile as a particle under constant velocity. Once a problem has been modeled, it is no longer about an automobile. It's about a particle undergoing certain type of motion that we have studied before. All analysis models we will develop are based on 4 fundamental simplification models. First is the particle model. Later, we will see analysis models based on simplification models of system, rigid object, and wave. When solving a problem, avoid the equation mining. That is, avoid browsing through the chapter looking for an equation that contains the unknown variable that is requested for the problem. Sometimes this is appropriate, especially when we're doing some of the equations of motion, but sometimes it can get you in trouble because it won't solve the problem that you're wanting to solve. Instead of equation mining, the first step is to identify the analysis model that is appropriate for the problem. Think carefully about what is going on in the problem and match it to the situation you've seen before. Once the analysis model is identified, a small number of equations appropriate for that model sometimes will be used. Sometimes only one equation. The model tells you which equation or equations to use for mathematical representation. Okay. Okay. Imagine a particle moving with constant velocity. The model of the particle under constant velocity can be applied in any situation in which the entity can be modeled as a particle moving with constant velocity. Remember how we talked about the car moving? We could say, well, use the center like the door handle of the front door. That you can use that as its center position. If the velocity of the particle is constant, then the instantaneous velocity at any instant during the time interval is the average velocity over the interval. Vx equals Vx average. Substitute Vx for Vx average, so you get Vx equals delta x over delta t. You know, it's the Vx average, and if it's at constant velocity, the Vx equals the Vx average. Using the definition of delta x, rewrite the equation. Delta x equals x final minus x initial. So that becomes Vx equals x final minus x initial over delta t. Then, if we solve for x final, the position of the particle given by the sum of original position x sub I at time t equals 0 plus displacement Vx delta t that occurs during the time interval delta t. Usually choose time at beginning of the interval to be t equals 0 and time at the end of the interval to be t final equal t. So we end up x final the final position is equal to initial position plus the constant velocity times the time that you're traveling for a constant Vx. Remember, this is only for a constant V. And we're only doing it in one dimension, so it's along the horizontal axis. Okay. Whenever an analysis model is a particle under constant velocity, you can immediately use these equations. V sub x equals delta x over delta t, and x final equals x initial plus Vx times t for constant Vx. This is not going to work for constant acceleration. We'll get to those later. Okay, this is a graphical representation of a particle under constant velocity. Notice that the slope, notice the slope in the position versus time graph. It's constant. It equals the magnitude of the velocity. The mathematical representation of a particle under constant velocity, it gives you the equation x equals xi plus vit. Okay, the slope of the straight line vx and y-intercept equals x sub I in both representations. In the opening storyline on page 20 about the equidistant telephone poles, the car was a particle under constant velocity, and it was a model represented by a part of the motion taking place at fixed speed. You found in the storyline that time intervals between poles were always the same in this case. Okay. Let's look at some examples. A kinesiologist is studying the biomechanics of the human body. Kinesiology is the study of the movement of the human body. Notice the connection to the word kinematics. She determines the velocity of an experimental subject while he runs along a straight line at a constant rate. The kinesiologist starts the stopwatch at the moment the runner passes a given point and stops it after the runner has passed another point 20 meters away. The time interval indicated on the stopwatch is 4 seconds. Okay. What is the runner's velocity? We model the moving runner as a particle because the size of the runner and the movement of arms and legs is unnecessary details. Because the problem states that the subject runs at a constant rate, a constant velocity, we can model him as a particle under constant velocity. Having identified the model, we can use this equation to find the constant velocity of the runner. If x initial is 0 and x final is 20 meters and the duration is 4 seconds, we get 20 meters divided by 4 seconds, that's 5 meters per second. Okay. Use this equation and the velocity found in part A to find the position of the particle at time t equals 10 seconds. So x final equals x initial plus vxt equals 0 plus 5 meters per second times 10 seconds equals 50 meters. As a result, for part A, a reasonable speed for a human. How does it compare to the world record speeds in the 100-meter and 200-meter sprints? I mean, a good sprinter can run 100 meters in about 10 seconds, so that's about 10 meters per second. Notice that the value in part B is more than twice that of the 20-meter position at which the stopwatch was stopped. Is this value consistent with the time of 10 seconds being more than twice the time of 4 seconds? Yes. Okay. Let's look at some more. A particle under constant velocity moves with constant speed along a straight line. Consider a particle moving with constant speed through a distance d along the curved path. A change in direction of motion signifies a change in velocity. Remember, velocity is a magnitude and a direction. Even though the constant speed, there's a change in the speed vector. There's a change in the velocity, really. The particle moving along a curved path can be represented with the model of a particle under constant speed. V average is replaced by a constant speed V. Imagine the particle moving at a constant speed of 5 meters per second in a circle with a radius of 10 meters. Calculate the time for one trip around the circle. Okay, if the radius is 10 meters, then the distance of the circle is 2 pi r, which is, that's why they have 2 pi r times 10 meters divided by 5 meters per second, and it's 12.6 seconds to make a round trip. Okay? Now, imagine a moving object that can be modeled as a particle. If it moves at a constant speed through a displacement delta x in a straight line in a time interval delta t, its constant velocity is Vx equals delta x over delta t. The position of the particle as a function of time is given by x final equals x initial plus Vx sub t. You can see that the particle, there's equidistant spacing between the little kind of reddish, pinkish balls, and the velocity vectors, the red arrows, are all the same size and all going in the same direction. Examples of particles under constant velocity would be a meteoroid traveling through gravity-free space, a car traveling at a constant speed on a straight highway, a runner traveling at a constant speed on a perfectly straight path, and an object moving at terminal speed through a viscous medium. Okay. Now, if it moves at constant speed through a distance d along a straight line or a curved path in a time interval delta t, its constant speed is v equals d over delta t, distance over delta t. A planet, examples would be a planet traveling around a perfectly circular orbit, a car traveling at a constant speed on a curved racetrack, a runner traveling at a constant speed on a curved path, or a charged particle moving through a uniform magnetic field. When you get to the second semester, you'll see how they charged particles move in helical paths in a magnetic field. Okay, with that, we're going to stop section 2.3, and the next will be a one-slide presentation on the approach to problem solving.